Hi, my name is Adam Zufall. I'm a graduate student here at the UC Davis Center for Space Exploration Research, and I wanted to share how I performed TVAC, or thermal vacuum testing, on a satellite payload I built in hopes that it would be helpful for other universities or other small satellite developers. Let's discuss why TVAC testing is necessary. So, in atmosphere, airflow allows electronics to maintain a consistent temperature. Without air, the only path for heat to enter or leave your electronics is through whatever metal allows for conduction. So, for high altitude balloons or for spacecraft in orbit, there's so little air that your electronics can either get too hot or too cold. So, TVAC testing lets us assess whether that will be an issue and then adjust our designs accordingly. Before doing any thermal testing, you should consider the thermal requirements of your electronics. My payload consists of a computer and a PCB with a few coin cell batteries. Again, that will be on this PCB here and on the backside. So I have two primary concerns. Number one is that my computer will get too hot, and it will definitely be generating the most heat, a few watts. And above 80 degrees Celsius, the computer will start to throttle itself. And if you get much further past that, you could actually damage the computer. Charging the batteries will also generate some heat from these charging ICs, but that is relatively small compared to the heat of the computer. Speaking of batteries, my second concern is that these batteries will get too cold. If batteries get below, again, these are lithium cells, get below about 10 degrees Celsius and you go to charge them, that can result in lithium plating, which drastically reduces the lifespan of your cells. So those are the two things that I want to address with my testing, is seeing if the computer gets too hot and seeing if the batteries get too cold. And that's also influenced by how heat will actually move through this system. I know the heat being generated by the computer will move along these GPIO pins, which are also how it connects to the battery board. But the only way for heat to leave the system is through these standoffs, which eventually connect to the spacecraft itself. So I'm going to want to replicate that sort of situation in my testing, which we will discuss later in this video. For the TVAC testing, we will first pump down this vacuum chamber, and then I will either put ice and cold water or boiling water into this tub to manipulate the temperature of the chamber. But before we dive into the test, let's go over this equipment. So this is the vacuum chamber. It is designed for degassing epoxies, and you can get them online for $100 or $200. They go down to just a few percent of an atmosphere, which is definitely not enough for hard vacuum space applications. But for this test is enough to give us a good idea of how the electronics will respond when they're not able to convect their heat away in air. It is pumped down by this vacuum pump, which this particular pump is definitely overkill. You can get cheaper pumps online, again, for degassing epoxies or those used by like HVAC professionals. And again, those pumps would cost a few $100s. This pump is definitely more than you need. The other equipment I have for the test is a power bank. These use 18650 cells and provides the 5 volts that the payload needs to run. And the payload never pulls more than like an amp, so those cells can power the test for several hours. I have a length of tubing that's useful for making a siphon to pump water out of the tub, a mug for scooping ice, an electric kettle for boiling water, and a kitchen thermometer for measuring the water temperature. You can see that I put the chamber on these blocks of wood. That's to let water get underneath the chamber so that we have nice thermal distribution across the chamber. This is just an overflow that I've capped, but then buckets to catch any water that leaks. So this is the equipment that we will be using to perform the test. I want to take a moment to think about how you're placing your electronics in the chamber. So for the payload, I want there to be good thermal contact that mimics how it will be mounted in the spacecraft as close as possible. So again, you want like the lengths of these standoffs to match what would be used in flight, and you want there to be good thermal contact with the chamber. For the batteries that are running the experiment, I don't want those batteries to get too hot or too cold. So I've placed them on an insulative pad and then actually placed them on a little cardboard box again, so that there's very little thermal transfer between the chamber and those batteries, so they don't get too hot or too cold. To collect the temperature data during these tests, there are four different sensors. The first is on the computer itself, which is the best way to see if the computer is getting too hot. And then we have three sensors on the battery board placed near where those batteries are, again, to measure whether those batteries are getting too cold. And then I ran four different tests. The first one was in air at room temperature. That is just operating the payload on the lab bench, making no changes, just to establish a baseline. The second test is in vacuum at room temperature. So that's putting it in the chamber, sucking out the air to see how much warmer are things going to get once you no longer have air convecting that heat away. Then I run the cold case in vacuum. For me, cold case is around 0 degrees Celsius. So I'm going to use melting ice to achieve those temperatures. Then I'll run the hot case in vacuum. For me, that's around 40 degrees Celsius. And I'm going to use boiling water to achieve those temperatures. A note for high altitude balloons, they can typically get much colder in the upper reaches of the atmosphere, down to like -50 degrees Celsius. So you might want to even consider using dry ice to achieve those temperatures. I have two important warnings before we dive into the test. The first is that water vapor will damage your pump. So it's really important that you seal and pump down that chamber before you start cooling it. Otherwise, fresh air could cool off, water vapor could condense, and too much water vapor getting into that pump will damage it. So you need to pump down the chamber with room temperature dry air. The second thing is that condensate will damage your electronics. So if you're running the cold case, before you end that test and you unseal your chamber and expose it to ambient air again, you need to warm up those electronics. Now we're ready to begin the test. So first, we would power on our electronics and place them into the chamber. I won't be doing that for this demonstration, but again, suppose that the electronics are powered, the software is running, and it's collecting data as it would be in the test. Now, the next step is to put the lid on. With the lid on, you want to go around and make sure that it's properly seated all the way around the chamber and that there's not a lot of overhang or underhang anywhere. And so it's looking pretty good. Notice that the valves are open. This is on purpose because the first thing we need to do is run the pump with the valves open for about 5 minutes so that the vacuum pump can actually come up to temperature and warm up. Before I start running the vacuum pump, I do want to check the oil gauge, and you can see that the level is between those two arrows, so that's good. And now I'm going to let the pump run for about 5 minutes and warm up before the next step. While the vacuum pump is warming up, you'll notice that the oil level has dropped, but it's still above that arrow. And if you look real close, you might be able to see the oil bubbles actually rising up. Sorry, air bubbles rising up out of the oil. So again, we want all these little bubbles that are currently in the oil to come out of solution. And once the bubbles are stopped forming, the vacuum pump has finished. Now that the vacuum pump has been running for 5 minutes to warm up, now is when we actually close the outer valve, this one on the right, that will seal the chamber off from the ambient atmosphere. And you can see now the pressure in the chamber will start dropping. So we will let the chamber continue dropping down to pressure and let the pump run for about 5-10 minutes, just until this gauge completely stops moving and the pressure reaches equilibrium. While the pressure is dropping in the chamber, because it's sealed off from the outside atmosphere and no more air is getting in there, we can also start reducing the temperature by adding ice to the chamber. So the chamber is still pumping down. The arrow has stopped moving, but I'm probably going to give it another 5 minutes or so after that point to make sure we get as far down as we can. I've started adding ice, and now I will also add water to make sure that, again, that cold ice water mixture is completely surrounding the chamber. You can see now that I added the water that actually quite a bit of ice melted, just bringing the water down to temperature. So I would recommend you pre-chill your water. Again, if you want to get down to temperature as quickly as possible. I didn't have quite enough ice today to do that, but it's a good idea to actually mix ice and water in your buckets for adding it to the chamber. So now the pump has been running for about 10 minutes with the chamber sealed, and the pressure gauge is no longer changing. So now we're ready to seal off the chamber and turn off the pump. It's very important that you do it in this order. You first close this valve and then you turn off the pump. If you do it in the opposite order, you can actually pull oil from the pump back up your hose, and that could damage your pump or contaminate your electronics. So the first thing we do is we close the inner valve to seal off the chamber. So now the chamber is isolated and it is safe to turn off the pump. So now our setup is complete. We are currently running the cold case. If I had more ice, I would continue to add ice to the tub as it melts and even kind of pile up ice on the sides of the chamber to make sure we get that chamber as cold as possible. And we just run the test until we're satisfied with however long we want the electronics to be at that temperature. Again, for my testing, it usually reached equilibrium after an hour or so. But again, you'll want to confirm that with your own measurements. Suppose that this has been running in the cold case for an hour, maybe 4 hours, however long you want to run that test, and you're ready to run the hot case. The first thing you're going to do is you're going to scoop out all of that ice, and then you're going to start replacing it with boiling water until it comes up to temperature. So let's do that. Something that can be really handy is using this little length of tubing as a siphon to help drain the tub of excess water. And that's just much more convenient than scooping it out by hand. After adding a few liters of boiling water, you can see the water temperature is rising. It's not quite at 40 C, but it's close. It is still colder at the bottom of the tub, which would be a problem. But again, as we continue to add boiling water and let it mix, it will all come up to temperature. While you're running the hot case, you'll need to continuously monitor, and every 10-15 minutes or so, remove some of the cool water and add more boiling water. And you can generally maintain a good water temperature to within a couple degrees. Now I'm ready to finish the test and unseal the chamber. Remember, if you're running the cold case, you need to let everything come back up to room temperature. But since I was running the hot case, everything is already warm enough to unseal the chamber and not worry about condensate. So you're going to open the outer valve, and you're just going to open it a little bit. So you can hear the air starting to rush back in, and the pressure will start to drop. You don't want to fully open it right away because that could damage the filter by air rushing in too quickly. But open it up, let the pressure start dropping, and slowly open that valve to let air back into the chamber. And the chamber will come to equilibrium. And once the chamber has reached atmospheric pressure again, then you can open up the inner valve that leads to the vacuum pump. And you want to do it in this order again so that you don't damage the pump by drawing oil back up the line. After recording all the data, you can see the temperature of your electronics over time and how long it takes to settle to various temperatures. Looking at this plot, the horizontal axis is time in minutes, the vertical axis is temperature in degrees Celsius. The green lines is when I was running the payload on the bench in air. The red line is when I was running the payload in vacuum, but still at room temperature. And then the blue lines are when I was running the payload in vacuum, first the cold case and then the hot case. The long-term trend is again it settling into the temperature that it would reach in each of those cases. The short-term oscillations are caused by when the battery is charging and discharging. Again, the charging IC generates some heat. You can also see that one of the batteries is typically higher than the other two. That's because it's closer to the computer, which is generating a lot of heat. And what temperatures you care about, again, will really depend on what your payload is. But this is the data you need to make those decisions. And in our case, we weren't quite happy with how cold the batteries were getting, so we ended up adding a resistive heater to make sure our batteries never got too cold. So this concludes my brief explanation of our TVAC testing. I hope it's helpful to you on your projects. And if you're a high school or university student, feel free to look me up in the UC Davis student directory and send me an email if you have more questions. Thank you. Have a good rest of your day.